Okay. That makes sense? Pretty clear? Okay, one more. 5 over 4 plus 3x. And you know what? I think y'all are ready for this. Let's do this. Let's go 5x to the 4th over 4 plus 3x. All right. So that x to the 4th on top is a problem, right? So we're going to do it exactly the way we did before in the previous problem. We're going to peel the 5 times x to the 4th out front, and then we're going to be left with 1 over 4 plus 3x on the bottom. Is that all right? We could do that. You want to do that? We could do 5x to the 4th times 1 over 4. Well, you know what? No, I'm not going to do that yet. Because I need that to look like 1 minus u, right? 1 minus u, not 4 minus u. Factor a 4 out. So I'm going to pull a 4 out, and when I do that, I get a 1 plus 3/4 x. Do y'all agree with that? So I pull the 4 out of the denominator. Something happened. Yeah, they might be resetting the board. No? Okay.
Is the top one? I was wondering, is the top female?
No.
What's the S?
For Fabiano.
Oh.
Male versus female. No. It's 2018. I don't think you can do that. Okay. Okay, so I'm getting closer, right? I'm getting closer. Okay, that's out there, right? And then now I'm going to rewrite that as 1 over, now 1 minus negative 3/4 x. So y'all were all comfortable with me pulling the 4 out and making that 3/4?
Where'd the 1/4 go?
Oh yeah, the 5/4. So this 4 came out under here. All right, we have it. We've got 1 over 1 minus u. So long as the absolute value of this is less than 1, I can now turn it into this power series. It'll be 5/4 x to the 4th sum n equals 0 to infinity of negative 3/4 x to the n. Agree?
So it doesn't matter the fact of the x to the 4th. Like you strictly only want to try to get that 1 minus the.
It doesn't matter that what?
Like that x to the 4th is there.
We're about to deal with that. Yeah, we're about to deal with it. So remember this sum right here. Take a look at this sum. The only thing that's changing in this sum is n, right? Okay, this right here, think about, you can look at it this way. This, when we add this up, it's going to be something plus something plus something, right? And so this out here would just distribute to each one of those, wouldn't it? And that's what I'm about to do, all right? But let me first finish writing out what's in here. What happened? Some pretty impressive power series, isn't it? I thought y'all were cheering for the power series. Yes. It's pretty sad when the chess game over here is more exciting than the power series, but it's like y'all have like never played chess in your life. You don't even know, like you want to like play checkers here and stuff, and this is more interesting than this. Okay, so all I did here was I split this up into 2 pieces, right? just to make it look like a power series. But now I've got to bring that x to the fourth back in. So watch what happens here. Sum n equals 0 to infinity. 5/4 comes in. Negative 3/4 to the n. And then check this out. X to the n. Any ideas? Plus 4, good. Plus 4. Because you're doing x to the n and you're bringing an x to the fourth in, right? So you're doing x to the n times x to the fourth, add the exponents, you get n plus 4. There's your power series. Oh, so this is significant. That's a winning position right there. So why? So either black's going to resign or run out of time. Well, what? Maybe not. Okay. Now this only holds if what? If absolute value of negative 3/4 x is less than 1. Okay. Yes?
What happened to that second negative?
Where?
Because on the first one, when we first pulled it out for those two negatives, and when we put it into the sum, how come we only have one?
Okay, because I'm using a formula. I'm using the formula is that if you have 1 over 1 minus u, that this becomes sum n equals 0 to infinity of u to the n. So look at this is 1 minus u. This is u, right? So that u goes right here. That's your u.
Okay, so then that second negative, we just kind of just throw it away.
This negative is part of the formula.
It's just a formula.
So it's 1, right? Minus, minus, and then that's u, and that the u goes in.
Oh, okay.
It's like just take that and stick it right there.
Oh.
Got it? Okay. Oh, so like, I don't know. I'm not even going to look over there anymore. Somebody's going to win that one. All right. Well, I wanted to see what happened on that first game, but sorry. Yeah. Stay tuned. Okay, one more of these. 1 over 1 plus x to the fifth. Expresses a power series. I can rewrite this as 1 over 1 minus negative x to the fifth, like that, right? Which would be sum n equals 0 to infinity of negative x to the fifth to the n. Which I could rewrite as sum n equals 0 to infinity, negative 1 to the n, and then x to the 5n. So what I did here is I rewrote this in here as negative 1 times x to the fifth, and then to the n. So I rewrote that as this, and then I did the n on the negative 1, and then I did x to the fifth to the n. You multiply the exponents and you get that. Right? It's alternating, yeah, but this is the power series right here. This is the power series that represents this expression, so long as what? This only holds if what? All right, let's continue. We're still in the same section. I think that you would agree that what I've shown you so far, we can convert some functions into power series, but they have to look like a certain thing, right? The ultimate goal would be, hey, somebody gives me a function, any function, can you convert it to a power series? That's the ultimate goal, all right? We're not there yet. So I now need to talk about differentiation of power series. So we call this term by term differentiation. And you'll see why. So what if, suppose we have some power series with radius of convergence greater than 0. I didn't mention this earlier. I should mention this. Do you all remember what the three possibilities were when you have a power series in terms of convergence? What the three possible outcomes are? Only at x equals a it converges? All real numbers or some interval, right? So let me ask you, if it only converges at x equals a, let's write these down, or this was everywhere, or it was some interval, right? I don't know, maybe it's like one endpoint, not the other. In this case right here, would you agree that the radius of convergence would be infinite? Like if it converges everywhere, then the radius out both directions would be everything, right? And then right here, do you agree that the radius of convergence would be some number? Some constant? But what about if you have, it's only at one point? The radius would be 0, okay? Which means you're standing at the center, it converges there, but you can't go to left or right. So these are our three outcomes: a single point, entire number line, interval. In those cases, the radius of convergence is 0, infinity, or some number. So we're saying here, let's say that you have a power series with a positive radius of convergence, which means that it's one of these two cases. All right? If we start with that, then let's figure out what the derivative of this would be. And you know what? Let's call this f of x. Let's call this f of x. Let f of x be this. Let's try and find the derivative of this function.
Product rule.
Well, do we need the product rule?
Oh, that's a constant.
Well, let's rewrite f of x first. What is f of x? Before we take the derivative, let's just start plugging in values here. So we would get 0 goes in for n, so we get c sub 0, and then all of this to the 0 would be 1, okay? So plus c sub 1 and then x minus a, plus c sub 2 x minus a squared, plus c sub 3 x minus a cubed, right? Yes, yes? Yeah? Plus we'll do one more, c sub 4 x minus a to the 4th. So that's me writing out the first, I don't know, 5 pieces of that power series. Let's differentiate it with respect to x. So what's the derivative of a constant? 0, right? Okay. Now, plus, what's the derivative of this here? Well, that's a constant, right? But it's attached to this. What's the derivative of that? 1, right? Because the derivative of x is 1, derivative of a is 0, because a is a constant. With me? So this should just be 1 times that. So we just get c sub 1. Plus, now, what about this one? Be careful. C sub 2 is going to stay, right? But then what? 2, this power rule, right? 2 comes out. This to the first power times the derivative of what's inside, which is 1. So shouldn't this just be 2 c sub 2 times x minus a? Agree? Plus, what would the next one be? 3 comes out, 3c sub 3, x minus a squared. And the last one, 4a sub 4, x minus a cubed plus, and then that pattern would continue. Do you all agree with that? Okay. Now, can you help me take that expression and write it back as a power series? Let me help you. I want you to start this power series at 1. So look at your C's first. You're going to have C sub 1, C sub 2, C sub 3, C sub... hold on. Whoa. No one caught that. That's supposed to be C sub 4. C sub 4 right there. So we're just going to have in our formula C sub n. Now what about the number in front? 1, 2, 3, 4. So that's just n in front. And then what about the x minus a powers here? X minus a to the what? N minus 1. Holy shit, it is the derivative of this, isn't it? Look at this. All it is if I told you take the derivative of that right there, you'd bring the n out, wouldn't you? And then these would stay and then take 1 away from that, right? The only real difference right now is that this index is starting at 1, right? What if I started it at 0? Would the formula still work? Because that right there. So if I started at 0, that's going to be 0. So that piece wouldn't even count. And then after you get to 1, it's going to pick up. All right? No, you can't start at negative 1. Yeah. So this is the derivative of that. Or, if you like, you can do this. X minus a to the n minus 1. Okay? Either started at 0 or at 1. It works both ways. Pretty cool, huh? All right. What about the antiderivative then? So what about integration of power series? Term by term integration. So we're going to start off with the same power series, but this time I want us to find the antiderivative. Does your gut tell you that it's just going to be like what you think it's going to be, like the power rule backwards? Let's see. So here's the power series we're looking at. We want to find the antiderivative. I've written out the power series. Now let's do the integral of each one of these. So the antiderivative of this is equal to, what's the antiderivative of a constant? Constant times x. So c sub 0 times x, right? Okay, now I'm about to do something that's a little weird. Just see if you follow me. Is it all right if I do the constant times x minus a? Why is that still okay? Let me try and explain it. When I distribute this through, I'm going to get the constant times x, like I said, right? What about when I do c sub 0 times negative a? That's just a number, right? A constant? I don't know what it is, but I'm integrating. Aren't I going to have a plus constant out here anyway? So that's not incorrect for me to put that, because I'm off by a constant to begin with, because I'm integrating. The reason I put it there is so that it matches everything else. Yes?
So would it be incorrect not to put it?
It would not look like the rest of these are going to look.
Yeah, but I'm saying would it be wrong?
Well, I want us to establish a pattern. Okay, so we can come up with a formula. So I need this x minus a here to make it look like the rest. Okay, so what about this one? If I asked you the antiderivative of x minus 2, right?
You just do them separate, so
It'd be 1/2 x squared minus 2x plus c, right? Plus c. And then what could we do here? Factor out an x. Like that.
Why is it?
Pardon me?
Factor out of 1/2 x.
What did I? Oh yeah, I forgot the 1/2 in here. Sorry, 1/2. Yeah, but I want to keep the 2, so let's just do it this way: 1/2, like that. Right? So, what would we do here?
For 1.
I'm trying to figure out what the antiderivative of this piece would be.
Well, wouldn't you do will it be the x to the n plus 1, so it'd be 1.
Let me do it this way. Watch. Let me do it this way because time. All right. Let me do it this way. Let's call this. This is what we're trying to find the antiderivative of, right?
Yes.
Let's just do a real quick u substitution, even though we don't need it. If I let u be x minus 2, du is dx. Agree? Then this integral becomes the integral of u du, right? Which is 1/2 u squared plus a constant, which is 1/2 u, which was x minus 2 squared. Right? Okay. This right here, we could do the same thing if this were x minus a. Right? So x minus a, this would be x minus a. So we would have this, wouldn't we? So do you agree that this right here, this one, sorry, we would, this is a constant, it's going to come for the ride. The antiderivative of that would be 1/2 this squared.
So it'd be 1/2 c.
So 1/2 c1 times x minus a squared. And then I could do that for each of these, couldn't I? If I change this to squared, it would just be u, and then this would be u squared, and we integrate 1/3 u cubed. So all of these are going to go the same way. So what's my next one? 1/3 c sub 2 x minus a cubed. One more. 1/4 c sub 3 x minus a to the 4th plus dot dot dot. So as a formula, this would be sum. Let's see if we can start it at 0. Let's take care of the c's first. C sub 0, C sub 1, C sub 2, right? So those are going to be just C sub n. Now what's in front of each of these? This is, we can look at this as 1 over 1, 1 over 2, 1 over 3, 1 over 4. So this is going to be 1 over n plus 1. Remember, because we're starting at 0. So plug in n plus 1. Wow, deja vu. Whoa. That was an intense one.
You need a vacation.
That's still part of the deja vu. That's weird. Your response is even... I need stronger coffee. All right. Okay, so far this okay? Now that takes care of this. Now what about this part? All of these. 1, 2, 3. Isn't that the same as what's happening here? So x minus a to the n plus 1. And look at that. I mean, that's exactly what we would have expected. Like if you focus your attention on just this, because the constant here doesn't matter, if I asked you for the antiderivative of like x to the n, you'd say 1 over n plus 1, x to the n plus 1. Well, that's what we have here. 1 over n plus 1, x to the n plus 1. Right? Okay. So if somebody provides us a power series, we can now differentiate it and we can now integrate it if we needed to, right? If we needed to.
If it started with 1, would that change?
Okay, so if it starts at 1, my formula changes. Yeah, you can't start this at 1 now and leave it. Because if I start at 1, this is going to be a 2. So we wouldn't pick this piece up. But you need that piece. All right, now let's see. This whole thing was just to show you that if somebody gives you a power series, you are free to integrate it or differentiate it at will using those formulas. Let's see if I can do this one. Express as a power series.
Are those the only two integration techniques we need to use on power series?
Those integration differentiation?
Well, I mean, like the power rule for integration.
Yeah, because so when it comes to power series, differentiating is super easy and integrating is super easy. Why? Because they're all powers of x. So integration and differentiation are easy, which is what's going to make e to the negative x squared easy. If we can turn that into a power series, integrating it's no problem, right? Okay, so this is back to what we just did. You know how we were doing those problems? It was like, I gave you a problem and I asked you to turn it into a power series. We were doing these like 1 over 1 plus 3x, something like that. So turn that into a power series. But then I said, hey, but we're very limited because this has to look a certain way for us to do this, right? So here's another problem. And I want us to turn that into a power series. Nobody in here is going to see how to do this. I don't think it's possible for anyone to see this. Yes? Okay, so you could try that. Let me do that because I figured someone was going to go down that road. That's a very smart idea. I think this is what you're suggesting. And then each of those is a power series, right? So let me continue with this. This is not going to be the way we do it, but let's continue with this. This is a good idea. The problem here is so long as the absolute value of x is less than 1. The problem is I want my answer to be a power series. One power series. What you have here is the product of two power series. And the question is, how do you put two power series together? Now, if this was addition, we can actually combine them together. But multiplication is a lot different because think about this. Isn't this right here something plus something plus something, right? Plus dot dot forever? That's what that is. And this one is something plus something plus something forever, right? And so the only way to put those together is to do an infinite expansion. It's not as easy as if this was a plus. Because if that was a plus, then we just put a plus and then it's all of them together, right? That's easier to do. Does that make sense? So we cannot do this.
And can't we only do, is it addition where they both have to converge?
That's right, and they would both have to be convergent. So we can't do that. Good try. I suspected someone would do that. This is the part that I don't think anyone's going to see. All right. So please recognize, if you could, that notice that we could find the power series for, right? If I asked you, what is the derivative of that? Okay, so let's see. Maybe we've forgotten how to do derivatives. This is the same as 1 minus x to the negative 1, right? That's what that is? And if I ask you to take derivative, what would that be? Negative 1, 1 minus x to the negative 2 times the derivative what's inside. Negative 1 again, which means 1 over 1 minus x squared. Do y'all agree? Okay. So what I'm saying here is that this right here, this expression that we're looking at, is actually equal to the derivative of that, right? That's what we just said? Right? Following me? So I had to recognize that, and that's what I said. No one's just going to sit here, oh yeah, that's just the derivative of 1 over 1 minus x. That's not going to happen. But now I've shown you that, you know this is on the table. This is fair game now. So this is the derivative of this. Now, what is this? Can I turn that into a power series? Absolutely. That is the sum n equals 0 to infinity of what? X to the n, right? That's what that is. But I want to do what to it? Take the derivative of it. And how do I take the derivative of a power series? We just did it, right? We said essentially, if you want to take the derivative, of that, we said all it amounts to, n equals 0 to infinity, all it amounts to is doing the sum and starting it at 1 or 0, right? But I'm going to start it at 1. Of what? N times c sub n x minus a to the n minus 1. Isn't that what it is? Yes. We just established that in the previous step, that really it is just a power rule. N comes out, n subtract 1, except that that index, I'm going to start it at 1 instead of 0. So this becomes sum n equals 1 to infinity of, that drops down, n x to the n minus 1.
Wait, you don't have to shift it because it's different? Like it's n equals 1 instead of n equals 0?
It's okay, I can leave it. That's a great question though. Do I have to put this back to 0? We can, not going to do it yet. I just want to make sure we all follow through with what happened there. Okay. Now, I would like for you to write out the first few terms of that. Just for me, let me know what this is. So if you plug in 1, you get 1. You get 1 plus 2x plus 3x squared 4x cubed, 5x to the 4th. That's it right there. What we're saying is that this is the same as this, so long as what? If the absolute value of x is less than 1, because, right, that was our u right there. That means if you were right now, if you gave me a number between less absolute value less 1, like if you gave me 0.2, okay, and I plug 0.2 right here, get 1 minus 0.2 is 0.8, and I square it and I do 1 divided by that, that answer would be the same as doing 1 plus 2 times 0.2 plus 3 times 0.2 squared plus 4 times 0.2 cubed, and so on and so forth. This right here would converge to that same answer. Now, would you ever want to do that? Probably not, because that's a lot easier to just plug 0.2 into this, right? Right? But as we're going to see, there are functions that when you actually go to your calculator, like right now, if you were to actually type in into your calculator sine of 2, what is your calculator doing? Doesn't matter. I don't care what that is, radians or degrees. Let me put it this way. If I go to my calculator and I type in 1 over 1 minus, let's say, 0.2, and then squared, my calculator can do this. It's just basic arithmetic, isn't it? It can do the arithmetic on this, right? Yeah. But if I come over here and let's do sine of 0.2 so I can keep it consistent. If I do sine of 0.2 here, what is my calculator doing? No, well, kind of, but your calculator in any computer can only do what? Addition, subtraction, multiplication, and division. That's it. Your computer is the basic 4 arithmetic operations. That's all it can do. So when you type sine of 0.2 in, Your calculator is not doing anything but addition, subtraction, multiplication, or division, which means that your calculator needs to know what sine of x means. All right? And sine of x to your calculator does not mean anything like, for us, it has to do with circles and triangles, and your calculator actually is using a power series to calculate this. There is some power series right here for this. Just like right here, if I plug in 0.2, I could do this instead. I would never want to, because that's much easier. But when you want to do this, how's your calculator going to do that? It's going to use its power series. So there is a power series for sine. There's a power series for cosine. There's a power series for tangent. For e to the x, for every function you know, there's a power series for it. That's our goal, is to try and, I throw a function up here, you give me its power series. That's our goal.
Those are all built into the calculator?
They're built in. Yep. Because look at these operations. All power series have a number and then an x and then raised to a power, right? This is all addition, subtraction, multiplication. That's all this is, right? Isn't x cubed just x times x times x, right? So that's multiplication. And your calculator can do these operations so fast that maybe your calculator has the power series for sine programmed into it, right? And then what it does is it takes the sum out to some predetermined tolerance. So whoever wrote the program for your calculator or computer will have told the computer, okay, you run this sum out a certain distance. And that's why when you get your answer, did anyone do sine of 0.2? No, no one did it? I don't know what it is, but if you do, that's all right, don't worry. Sine of 0.2, let's just say is 0.3456. What has your calculator done? It has run the sum and then stopped at some place.
Yeah.
It can't do an infinite sum, right? What is it?
It's like 0.1986.
0.1986. 6933 08. Anyone go further than that? But there's a setting in your calculator where you can set how many decimals you want it to go out. So if you set your calculator to go more decimals, it's actually going to run the series out further. Okay? That's what's happening. That's the mechanics of functions in a computer. I hope that makes sense. I'm trying to give this some credibility for later.
So calculators don't actually know what like trigonometric functions.
No.
They just don't know.
Nope. They don't know what it is. Right? So when you type into your calculator arcsine of arcsine of 1, your calculator is not sitting there going, okay, if I have a unit circle, right, I want to know where my y-coordinate's 1, okay, but it's an arcsine, so I can't be over here, so it's got to be pi over 2, right? No, it has a predetermined power series for this function. And so it just plugs x into that power series out to a certain position and stops, and then returns the value. All right, well, I think that's it for time. We are not through with this section. We were just starting to get into some interesting stuff. We only have 2 more class meetings. We have 2 more classes, and we have really one more. This section we need to finish, and the next section we need to finish, and that'll be it for chapter 8. But these last 2 sections are very dense, so do as much as you can on your homework this weekend. I would say for 8-6 homework, can you do any of it? Let's see. Yes, for your 8-6 homework, you can actually do the first 12 problems. Enjoy. Have a good weekend. Oh, does anyone know what happened with the first game?